Welcome everyone, I'm Stephen Hales, I'm the Head of Department in Computer Science, and as Head of Department it's one of my great pleasures, actually it's one of the great pleasures of the job, to be able to introduce people at their inaugurals. It's a celebration event, but it's also a reflection of achievement and the standing of people within the department. And the success of the department, the standing of the department, is built on individual achievement. It's a particular pleasure to introduce Tim because he's come up through the ranks. Tim was a PhD student here a few years ago now, but not just that though, but Tim represents an excellent example of how coming up through the ranks in academia, actually then putting a foot into industry and then working across that divide can be achieved, right? And successfully so. And as a department, that kind of relationship is super important to us. So, working across the divide, complementing each other is extremely, it's innovative, and it's a way that academia is going to have to develop further into the future, particularly computer science. So Tim's a senior staff member, senior research scientist, and the Open-Endedness Team Lead at Google DeepMind. He's already been through Meta as well as an area lead, but he's now also a professor of artificial intelligence in the AI Centre in CS. And that's what we're here to celebrate tonight. So that cross-divide activity and actually Tim's individual academic achievement in becoming a professor in the department. So it's with very great pleasure that I'm going to introduce Tim and ask him to come up and speak.
Thank you, Steve. Yeah, it's a pleasure to be here. It's fantastic to see so many people coming today, lots of family, friends, PhD students, colleagues, students. Thanks so much for coming and listening to my inaugural lecture on open-endedness and general intelligence. The thing I want to say right from the start is it's, I think, really not so much a celebration of me, but really a celebration of the fantastic PhD students and collaborators I got to work with. It is also a snapshot of them. There's more people missing, like master students and so on. So a lot of them are here as well. A lot of PhD students from our group. I saw Mikael, Akbir, Rob, Davide, and Laura. So after this lecture, when you join us for drinks, reach out to them, go to them, talk to them about their research as well, get to know them. And yeah, I got the pleasure to work with lots of people across different organizations, Meta AI and then Google DeepMind. But also this is a celebration of, I guess, our lab, but also more broadly the UCL Center for Artificial Intelligence. Because the majority of the students in my lab were actually funded by the Center for Doctoral Training and Foundational AI. So we're really grateful for the funding that we got through this center and the opportunity it gave to our students. And then we also really happy to work across different labs in the UK and internationally. So yeah, it's a celebration of that as well, and I think that's important to highlight. Okay, so I think it's fair to say that we're living through extraordinary times, and I'm pretty sure that almost every generation over the last hundreds of thousands of years have said that of themselves. If you've been living through the Industrial Revolution, that was probably a very, very exciting time. But now I think it is, at least to me, it really feels quite different. I mean, it feels like when I was starting a PhD, we were doing machine learning and a lot of good old-fashioned AI as well. And now the rate of progress is really astonishing. I find it really hard, and I see this with colleagues as well, we find it really hard to anticipate what might be possible with AI technology in the next 6 months, a year, or 2 years. It becomes very hard to predict. And just to give you a very incomplete and very brief history of AI, because we also have a number of people here who don't necessarily have a computer science or AI background, this kind of dream of creating an artificial intelligence is very old. If you look into Homer's Iliad, you can, for example, read that Hephaestus, the god of metalworking and sculpting and blacksmiths, created automatons of metal and servants of gold to help him in his course. If you look into Aristotle's Politics, you can also read, that even at that time they already foreshadowed automated tools that could at some point make labor unnecessary. And if you look into Gulliver's Travels by Jonathan Swift, he describes the engine with which even the most ignorant person might write books in philosophy, poetry, politics, laws, mathematics, theology, without the least assistance from genius or study. And we're getting there, right? We now have chatbots that can write poems, and it does pose a lot of also challenges for us in the department, right, in terms of how we should, for example, assess student achievements or exams. Obviously, it's not as as severe as it's written here. Okay, then of course, Alan Turing in 1950 published a paper on computing, machinery, and intelligence, in which he asked the questions, can machine think? He also introduced the imitation game, or the thing that now became known as the Turing test, a way to basically assess whether a human can be fooled by an AI to think that that AI is a human. And in 1956, a number of smart people came together to organize the Dartmouth Summer Research Project on AI, and it's believed that the term artificial intelligence was coined around that time by John McCarthy. And if you look into this proposal, you can read that they conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. And they will make an attempt to find how machines can use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and then also improve themselves. And at the time they thought that a significant advance can be made in one or more of these problems if a carefully selected group of people, scientists, come together and work for it over summer. And maybe that amuses us right now, this kind of optimism for making fast progress over the summer. It took, almost 70 years to actually get where we are right now from this point. But I think a lot of the things that they set themselves as goals here, right? They're obviously at the time were quite visionary, and are things we still try to, make more progress on. So then, in 1997, a chess AI called Deep Blue defeated the world champion Garry Kasparov by winning 2 games and drawing 3. This was a big moment for AI. This Deep Blue chess engine was able to simulate around 12 steps into the future for all basically possible moves. And then after that, it uses a heuristic to figure out whether the resulting board configuration is looking good or not. Right? So you can use heuristics like, is your queen still alive? How many pieces do you have left on the board? How are they roughly positioned? And from that, you can basically say, this looks maybe good, but it doesn't look so good. And Deep Blue was able to analyze 100 million moves per second. It was based on a search method on a supercluster, and was enough to beat the world's best player at chess. The thing to note here, though, is that Deep Blue wasn't learning anything. Right? It doesn't get better by playing more chess. All the knowledge that was required to basically beat human expert players and grandmasters in chess was built into the way this kind of brute force heuristic the search was implemented. Now we have a big shift, right? In 2013, and obviously also before already, but in 2013, DeepMind published a paper in Nature where they demonstrate that an autonomous AI can learn to play over 50 different Atari arcade video games using what's called deep reinforcement learning. Right? People before that already obviously did a lot of research on learning-based systems, but there's a really big difference, right, between this kind of chess AI and now actually a system that gets better by getting more experience and learning from that experience. And then in 2016, DeepMind's AlphaGo defeated one of the world's best Go players, Lee Sedol. And then in 2020, as all of you know, OpenAI released ChatGPT, All of these are learning-based systems. So one can now look into how are we doing in terms of the progress towards more and more capable AI. There was an interesting paper from last year on the levels of artificial general intelligence, the way they are, first of all, dividing up the field into narrow AI and general AI. Within the narrow AI, we then have different levels from 0 to 5. Level 0 would be a calculator, doesn't do anything necessarily smart. And then as you kind of go up the levels, you get AI that, for example, is quite good at filtering spam out of your email. Then AI that might actually be quite good at checking grammar for you and spelling. Clearly, my AI that I use on my laptop is better at grammar and spelling than I am, right? So this kind of gets into this kind of expert level where it's better than 90% of skilled humans in this kind of domain. And as you go further down or up the levels, you might at some point have a superhuman AI, such as AlphaZero, which is kind of the extension of AlphaGo, and that can also play chess. So at that point, we have basically AI that we know kind of is better at chess and Go than any human on Earth. And it doesn't look like we'll be able to catch up, right? So they transcended basically the capabilities of humans in these kind of narrow domains. And we can contrast that now with general intelligence. And what Morris defined in this paper is that general intelligence is intelligence in the right range of non-physical tasks, including metacognitive abilities like learning new skills. And generality here really refers to the breadth of an AI system's capabilities. So the range of tasks for which an AI system reaches a target performance threshold. Right, so we can now contrast this. I have another column on general AI, and here we are basically exactly at this point, according to this taxonomy. Right, we are at this level of emerging general intelligence. This is what these kind of chatbots are providing. So now we can ask the question, okay, why are we seeing this? Why are we there right now? And I think the important thing to know here is that before 2018, AI systems needed either significant hand engineering, such as the rule-based systems and search methods like Deep Blue, or large amounts of manually annotated training data, or a very dense reward signal in reinforcement learning where we really specify quite clearly what the system gets rewarded for when it tries to explore by itself. So all of this requires a lot of hand engineering, a lot of domain knowledge going into these systems. And since 2018, researchers have figured out a way to train these AI models basically without any human label data. I mean, the data still comes from humans, might be human text, but there's no extra annotation step where humans sat down and tried to, give it more structured data to learn from. Simply by letting the AI process massive amounts of unstructured data, such as texts, or nowadays also images and videos. And I guess the term that many of you have heard over the last 2 years are language models. They have been obviously around for a long time, but have become very popular in the last few years, at least in the public eye. And the way this works, just on a very, very high level, is that imagine you're an AI and you're learning basically language. And what you're given is some kind of text, and you're not given the text as a whole, you're given the text basically word by word. So let's say you're the AI, I give you the hunter, and now I'm asking you, okay, what's the next word? The most likely next word that should follow after these 2 words. And you might say something like jumped, or shot, or ran, or whatever, right? And then I tell you, well, the actual next word in the text that I'm seeing and you're not seeing is shot. And now you're going to adjust your weights or your parameters of the model such that in the future you're going to be more likely predicting shot after the hunter than, let's say, some other random word from the English language. And then after this word, I'm going to ask you again, right? What's most likely the next word? And now you might say something like dog, or cat, or deer, or bear. And then I'm telling you, well, the next word is actually sorry, it's actually an article. See how bad I am at grammar. So it should be an article, right? Or it could be something like, yeah, it should probably be an article. Maybe there's some other ways to go. And then, it should be maybe another animal like a fox or deer or dog or cat. And again, when the model sees this kind of next word, it's going to adjust its parameters such that in the future it's going to more likely predict at this point Fox than some kind of random other word. And I think the thing to note here is if you're only doing this, right, if your only task in life is to predict the next word, that's still an extremely rich training signal because you start to learn a lot about the world, such as grammar, right? Articles follow after this kind of word. Or you learn that, you know, hunters shoot generally foxes, and maybe not so often dogs and cats, right? Because these are domestic animals. So when you're getting really good at this, you start to learn actually a lot about how the world works. Okay, and what are these kind of parameters? What are these kind of models that we are training there? To make a very crude statement here, it's basically trying to simulate biological neurons. Biological neurons have a lot of details to it, and there's a lot of subtleties. I have very little knowledge about this, but on a high level, right, you have this kind of activation that travels to connect with other neurons through these kind of synapses, and when there's multiple connections and multiple activations coming from multiple neurons, right, then the neuron that we're talking about might get above some threshold and then also send out an information across this axis. And in AI, right now, what we use is a very, very crude approximation of this model. I mean, it's very simple. You have these neural activations represented by numbers. You have these weights that correspond to the connection, the strength of the connection to an output neuron based on these activations of the input neurons, and weighted by these weights here, the parameters, you produce an output activation. You might add some kind of transformation to this output, doesn't really matter so much. So what are the parameters of this model? It's these weights. So these are the things we want to learn. We want to adapt, basically, these weights such that given inputs, it produces the right output. And indeed, if you look into the cerebral cortex and the human brain, you would find that the biological neurons that humans have, they, at least in certain places, are structured in a quite hierarchical way. So you get these kind of different layers of biological neurons and how they're connected. And indeed, in the current AI systems that we're training, the current artificial neural networks, we also use these kind of hierarchies of simulated neurons. And as I said, what we're learning, basically what we're adjusting, are these kind of weights between these neurons, such that when we give it a training data, like the sentence I showed you before, and then asking it to predict the next word, we are feeding in the inputs. We let the neural network process basically these inputs, layer by layer, and then at the end we have an output layer that can correspond, for example, to a classification, or it can correspond to a regression signal. Doesn't really matter. It's going to, for example, try to predict, okay, the next word should be shot or should be false, or whatever. And then based on the signal, the error signal, we're going to propagate this error signal back layer by layer through this neural network and adjust the weight such that in the future the model gets better at predicting the right output given the given input. Okay, so I said since 2018, researchers figured out how to basically do this without necessarily a lot of human annotated training data by just reading text online. And you can look at basically the number of parameters, the size of these models that people were able to train since then. So in 2018, these models were around 100 million parameters. By 2020, there were already 10 billion parameters. And nowadays, we have models that are up to 2 trillion parameters. Right? And that means there's basically 2 trillion connections between these neurons. And all of these things are basically learned, these different things. I looked it up. So the human brain has around 100 billion neurons, I think. And on average, each neuron is connected to 1,000 other neurons. So we are basically 2 orders of magnitude off right now still. So human brains would have around 100 trillion connections, and we are at like 2 trillion connections right now. If you want to stay with this very crude, comparison between biological neurons and the artificial neural networks that we built. And if we look at current compute trends, then probably by the end of the decade we have neural networks, artificial neural networks that have also around 100 trillion connections. Okay, so if you do this at this massive scale, what you see is that the models get good at a lot of things. They can suddenly do a lot of things that were, I think, quite surprising to many of us. So you can ask the language model, or at this point we would call it a large language model, we can ask it to complete the following statement. The capital of UK is, and I would predict London. And we can ask it, to bake a cake you will need, and I would predict flour. Queen Elizabeth II was a trained mechanic. I didn't know this. In English, my name is Tim, German. Now it would start to predict the first word of the translation, and actually predicts not a word-by-word translation, right? It starts actually with ich, which is, it's like how you would say it. You wouldn't say mein Name is Tim, you would say ich heiße Tim. So it actually gets that as well. You can ask it something like this, right? What's 10 divided by 5 plus 2 times 3? And it gets that right. And just hold on a second and realize like what you need to know, right, to make this prediction. You need to know about the precedence of these mathematical operators. So I think it's quite astonishing. You can also ask it, all mammals are warm-blooded, and wildlings are mammals, wildlings are warm-blooded. And this is, again, quite surprising because wildlings doesn't exist. I made this up. Like, this is a word that doesn't exist. So it has to derive this basically from logical deduction. And it can do it if it sees a lot of these kind of examples online. And you can even give it Python programs that would be able to predict or interpret the output of such a Python program. And indeed, GPT 3.5 and GPT 4, they were both demonstrating pretty astonishing capabilities in terms of solving automatically university entry exams, right, in things like physics and chemistry and so on. Okay, so we are here, as I said, and now the question is, how do we get here, right? How can we move further up these kind of levels of general intelligence? And one of the things that we've been doing a lot in my lab here at UCL, but also at DeepMind, is taking inspiration from this emerging field of open-endedness research. So I already talked about general intelligence, now let's talk about open-endedness. Basically, the argument is that in machine learning for a long time, we've been trying to optimize towards a specific goal. We had a specific metric in the leaderboard or a specific reward signal that we wanted to get our AI to get better and better at just better at optimizing for, right? And the argument that open-endedness researchers like Ken Stanley make is that actually that seems a bit flawed because in life, like a lot of the things, we just have no idea in advance what we should be optimizing for. Like we need to find stepping stones that over time might lead to something useful. And one perfect example of this is biology and the evolution of life itself, right? So you look back for a billion years, and at some point, bacteria start, or cell organisms start to emerge, and bacteria, and then you get this kind of, at some point, you get this explosion of diversity. You get all of these different organisms, and then you get them further diversifying until you have this fantastic kind of modern kind of tree of life. And this is not just true for biological evolution. You can also look into technology itself. Right? If you look at helmets from the Middle Ages, and you look at like how these kind of helmets have been evolving over time, you get also a phylogenetic tree. And this is quite different to, I think, how we oftentimes do machine learning when we try to just optimize for one goal. And Kenneth Stanley tried to also basically put that into a demonstration, into a system. And what they came up with is this pig breeder system. The way this works is you're given a picture that's generated through some kind of process, some noise, and then you're selecting which of these images you like. So you say, oh, I like this image. And then it generates a variation of that image. Again, let's say 15 different variations, and then you can select which one you like most. And if you do this for many, many steps, then you can evolve or can generate an image like a skull in there. And indeed, you can generate a lot of really fantastic looking images, like images of things that look like a butterfly or an ant or a bear or lots of interesting things. But the really important point is that you can't plan for this in advance. There's no way for you to basically, starting from some kind of random looking image with like multiple variations, to deliberately generate, let's say, a clown face. It's going to be impossible for you. right? Because none of the stepping stones, none of the intermediate images look anything like the end product. Like to create, for example, this pigeon over here, you have to go through this thing over there. Like, there's no way for you to know this in advance that you have to do this. So the only thing you can do is basically explore, try out things, and see where you land. Okay, so that's open-endedness. Now, the question that I think I've been asking myself for the last 2 years, also prompted a lot by our PhD students in our lab, is to get to more generally capable AI, can we just go with language? Can we just scale up these kind of language models and we'll get there? Or do we have to do something else? So the question is, language enough, or training on static data sets on the internet of language, is that enough to get us to more and more generally capable AI? Or do we have to do something else? So for a moment, let's assume we have to do something else. And I think this is founded in a number of works over the last few decades. There's this study from Held and Hein where they have these two really poor kittens. They're really young kittens, basically just direct after birth. One of the kittens can walk around, it's this one, and the other one is in this like really weirdly looking cart. And this kitten moves around, and whenever it moves around, it would create a quite similar movement or symmetric movement on this side. So basically, both of these kittens see exactly the same things during their life, but one of them has been acting, the other one has been just passively watching. And then afterwards, they do some studies in terms of how well their perception has developed, and they find that the passive kitten basically hasn't really developed vision, whereas this active kitten was able to develop vision, although both of these kittens have seen exactly the same things, basically. Right, so there's an argument that we actually might need active learning in order to get agents or AIs to do something sensible. And this was actually reproduced in 2021 in reinforcement learning by Ostrovsky et al., where they show that for two kinds of environment, or for the same environment, training once passively and once actively makes a huge difference. If you're not active, if you're not making your own decisions, basically you're not going to learn something sensible. Okay, so let's assume for a moment language isn't enough. Well, then we have to do something that's called, or that falls into the formalism of reinforcement learning. We have to assume there's an agent. The agent can act in an environment, and then from the environment, the agent gets back an observation, we call that state, and potentially also a reward. So the environment might tell the agent, oh, this was something you did that was great, this was something that wasn't great. And just to say it already in this context back to open-endedness, once you assume this kind of reward, I think you're already solving a large part of the problem, because for most interesting problems like, how do you get a degree in computer science, there's not necessarily any kind of fine-grained reward function that guides you along all the way. Right? So once people say reward is enough, I think they already assume that there's a lot of knowledge put into this kind of system. Okay, so still, this has led to a lot of amazing progress over the last decade. As I said already, deep reinforcement learning was able to play Atari games. It's also used for playing Minecraft and other environments like NetTech and so on. So I think it's a lot of really interesting things that happen using deep reinforcement learning. But there's one thing that's really, I think, important when you think about creating a more generally capable agent. You can't think of that agent without at the same time thinking about the environment. Because the agent, the breadth and generality of that agent is going to be bottlenecked by the richness and the diversity of the environment that you train this agent in. Right? If you train an agent in chess or in Atari games, you will never be able to use that outside of these kind of simulation environments or games. It won't, do something clever for whatever problem you actually care about. In order to have that, you need to think of a really broad and rich and diverse environment in which you can train such a generally capable AI. And I think that was really nicely put into a quote, not in the context of AI, but much before that, by Alan Watts. He said that the relationship between the organism and the environment is transactional. The environment grows the organism, and the organism creates the environment. It isn't that organisms came into this world by accident or chance. This world is the sort of environment that grows organisms, and it has been that way from the beginning. So you basically have this kind of agent-environment dualism. You can't have these things separate. Like, it doesn't make sense, at least in my view. But at this point, I think we know the path to create more and more generally capable adaptive agents. We just did a study in 2023 at DeepMind called Adaptive Agents, and I think it's three things that have to come together. So one is this kind of really rich, diverse, interactive environment. The other one is to have a really large model, so a large artificial neural network parameterizing the agent. And then you have to glue these two things together using what's called automated curriculum learning. So let's look into that a little bit in detail. For a rich interactive environment, we can, for example, procedurally generate a lot of different games. So we did, I think we generated around 25 billion of these kind of problems. They range a lot of different things like physical manipulation, division of labor if it's a multi-agent system, information asymmetry, tool use, and so on. So you have a lot of very different tasks that this kind of agent has to learn from and master. And then you can use methods like prior-test library replay. This is work from Minxi Zhang and others in the group that tries to be clever of how to select what kind of a task to present when to the agent. So normally you would take these 25 billion problems and you would what we call uniformly sample from them. So you just take whichever problem from this massive set, and that you can think of as extremely inefficient, right? Because in the beginning of training, this agent doesn't know anything, so basically all of these tasks are going to be way too hard for the agent. So this is not useful. And later on, when the agent gets better and better, most of these tasks might be actually boring. They might be too easy. So what you want to do instead is you want to basically build this zone, this Goldilocks zone of not too easy, not too hard problems. And the way Minxi proposed to do this in 2021 is by having the agent predict how well it thinks it will do for a problem, and then comparing that with the empirical success it got by actually trying things out in the environment. And then there are basically four cases. One case is that the agent thinks it will do really badly, and it does really badly. The other one is that the agent thinks it will do really well, and it does really well. These are the two boring ones, right? Because the agent was right in terms of how well it thinks, how badly it thinks it will do. And then there are the two really interesting ones. One is it thinks it will do really well, and it actually does badly. That happens. It happened to me, I think, a few times during exams. And the other one is you think you'll do really badly, but somehow you actually didn't do so badly. Right? There was something you maybe tried out randomly, or something you figured out in the moment that worked. Then it's a question about how can you maybe repeat that success. So whenever you have one of these two interesting cases, what Minxi does is to save these kind of problems in a buffer, such that in the future we're not just randomly sampling problems, but we're going to sample them according sometimes to what are the interesting problems that we should revisit, right? The ones that were in this Goldilocks zone of not too easy, not too hard. And that, for all kinds of simulation environments, led to really stark improvement in terms of the capabilities and the breadth of the capabilities of the agents that we trained. Okay, and the last one, as I said, is a large model. So we tried different kind of sizes of these artificial neural networks in this kind of training environment, and we found that as the models get bigger and bigger, they get more and more capable. This is something that we see all over the place nowadays, that with more data, bigger model, things get better. So just to show you how this looks like, test time. So we have this agent. It's this little clock over here. And it has to, for example, craft a black cube, and there are certain rules that are hidden to the agent. You can't see those. It has to try them out, basically, through experimentation. And in the beginning, it randomly tries to put things together, and it actually triggers a dead-end rule, so it destroys this yellow sphere, and it can't create this black cube anymore. But then in a future episode, it actually figures somehow how to create this cube, and then in further future episodes, it's actually getting just more and more efficient at doing this. And what's important here is the video that you just saw. It's at test time. There's no learning anymore by the agent. There's no adaptation of the weights of the artificial neural network. All the learning that's happening is what we call in context. It's basically by the agent just observing its own behavior and then trying out different things at test time. Okay, so now the question is, given that we think we have the recipe, why don't we have like really general capable AI at this point? What's the bottleneck here now? Is it automated curriculum learning? So maybe we just lack more clever methods of like gluing together these like really humongous task distributions with these large models. And I think that's not the bottleneck, because we have a lot of ideas and a lot of results as well on like more sophisticated automated curriculum learning methods. For example, we have this method Excel by Jack Parker Holders and others, where we are not just randomly sampling problems and then keeping those that were interesting, we're actually actively mutating the problems to find more interesting problems in this Goldilocks zone of not too easy, not too hard. So you see this happening here at the top right? So it's kind of evolving more and more complex problems for the agent, always kind of tracking what the agent is currently capable of. And then you get to really interesting, very general behavior. So this kind of little simulated robot has to make its way all the way to the right there. And it's very challenging because it has to jump over these kind of obstacles. It has to not lose balance because otherwise it falls over and the episode is over. And it does learn really sophisticated behavior, like this, really exciting jump here at the end. So we have these kind of methods that are more and more capable in terms of the curriculum learning that we're automatically doing. We even have now versions, thanks to Mika Samler and others in the lab, that can extend that to multi-agent systems. So where you're not just trying to present the most challenging, let's say, environment to the agent, you're also presenting that with the most challenging co-player or opponent. And that can lead to really interesting, broadly capable skills in this kind of 2D driving simulation. I could watch this for hours, like this, it's taking over, it's trying to push the opponent off the road and all of that stuff. Obviously, none of that I think would be legal in Formula 1. So it's not automated curriculum learning. We have a lot of interesting ideas there. The other one would be maybe we just need larger models. Well, yes, like the models that we have here in 2023, they were up to 265 million parameters. We could scale that up to 1 billion, 10 billion, 100 billion, maybe a trillion. Like that isn't the bottleneck, we could do that. I think the bottleneck is having access to these rich interactive environments. And I would go as far as to say that progress in developing more generally capable embodied AI lags behind the successes that we see in these large language models right now, because handcrafted simulators are not and never will be rich and diverse enough. You can't have more and more engineers building more and more of these kind of simulation environments. You can't onboard more and more external games to get you a rich and diverse training distribution. And obviously, at this point, the bottleneck here is handcrafted, or the problem is handcrafted, right? I think we can't rely on human labor to kind of solve this for us. But instead, we could take a data-driven approach. We could look into learning simulators in which we then can train agents. And this is indeed something that people are starting to explore more and more. There's a startup in the UK called Wave AI, and they have cars driving around in London and UK. They collect all of this footage, all of these videos together also with the actions that human driver has performed. And then they can train what's called a world model. They can train a simulator that basically simulates driving around in London. And if you look very carefully, you can very quickly spot that this isn't the real world, that this is actually must be a learned simulation because there's some kind of inconsistencies. But if you squint at this, it looks actually quite impressive, I think. The problem is it only runs at, I think, a frame per second or less than that. And at the same time, we can look into what people are able to do just with video generation models. So this is OpenAI's Sora that came out a few months ago. All of the videos that you see here are generated by an AI. So none of this is real. And I think it is really impressive. Like, just have a look at it again. Right? Like it would be, I think, at this point for a human, not knowing this, looking at these videos, it becomes very hard to tell whether this is real or not. Specifically over here on the top right, if you look at the reflections and all of this, I think it's pretty impressive. Right, so on one hand, we get video generation models to, I think at this point, starting to generate videos that are almost indistinguishable from reality. And on the other hand, we can potentially train world models that can actually simulate not just generate a video, but where you can actually step in and you can actually try out things and do things and have with actions modify how the future is going to look like. Right, so Gaia is is a world model. It's trained on videos and actions. And what it gives you at test time, controllability on a frame level. You're not just generating a video, you actually, per frame, you can press an action and it would react to that. Whereas Sora is a video model, it's trained on video and text. And at the end of the day, you can't control much. You can describe what you want to see, and then it generates the video of what you asked it to generate. So what we did over the last year, and what we published earlier this year, is Genie. We learned a generative interactive environment just from videos that is then playable both by humans and AI agents. So we take internet-scale videos, we put them into our Genie model, and at the end, we're not just getting a model that generates a video, but we get something where we have an image or frame, then we select an action, and it would predict the next frame. Right? So it's a world model like Gaia, but it's trained without any actions. And this is crucial because now we can scale this up to all kinds of videos. So at training time again, the model only takes video data in. It tries to infer actions between frames, latent actions between frames. And then at test time, we prompt the model with an image that can be either an image, for example, generated by an AI. Right, this over here looks like a game, but it's actually not a real game. It's through a text-to-image generation model, we generated a screenshot of a game that doesn't exist. And then we give that to the Genie model, we provide actions, and now we can play that non-existing game. And as all these kind of models, we look into scaling properties. How does the model get better as we scale up the model size? So you can prompt that with a lot of different things. You can prompt that, as I said, with these synthetically generated images of games that don't exist. You could also prompt it with a sketch that you draw. You could even try to prompt that with a real-world photograph, and then you can see if you can play it, basically. So here, just shows you the kind of things we're able to do with this. None of the images I'm showing you are actual games. They are, as I said, all generated images from an AI, and then we feed that to Genie to actually play these games. And it allows us, through this way, to generate a humongous variety of different interactive experiences. And what's important is that these kind of latent actions, they're actually corresponding to semantically meaningful actions, and they're consistent across different generated experiences. So the same kind of action sequence, latent action sequence here, results in quite similar movement behavior in these kind of game-like experiences. When you train this at a certain scale, so if you use a large enough neural network and you train this on a lot of data, there are certain capabilities also emerging. Like, for example, this parallax animation. The model basically tries to give you some kind of illusion of 3D by basically making sure that objects in the foreground move faster than objects in the background. And as I said, you can also prompt that with photographs. For example, this is a little figurine on my desk that a team played with. So we give that to Genie, and then we try to jump off that platform, and that doesn't work as well. And as I said, you can prompt that with like sketches, hand-drawn sketches. You can prompt that even with video and with like other real-world images. And given the same starting frame, so this is again not an existing game, but something generated by an AI, we feed that frame we start from that frame. We let 4 different people play with this. They all can generate different behavior, different experiences. Right? So it's really controllable at this point. And what was really interesting to us is that it doesn't just work with these kind of 2D kind of game-like experiences, but we also tried this out for robotics. So we trained this model on videos of robot arms doing stuff, and then we get basically a learned simulator of manipulating this robot arm to do certain things. Right? So we again provided with a certain sequence of latent actions, and they would lead to similar behavior in different situations. And also really interesting to us, when we do this at a certain scale, it learns other aspects like the fact that certain objects are deformable. Right? So again, these are not real videos. These are all just imagined by the model, by us controlling this kind of imagined robot arm. And when we get to this kind of bag of chips and we're grabbing it, it actually does deform this bag of chips. Okay, and you can imagine how this can be useful now, right, to train more generally capable agents, because we kind of remove this bottleneck of getting rich and diverse interactive environments. So let's get back to this, this crossroads. So far we looked into, okay, maybe language isn't enough, we need to do more. But what if language is enough? Maybe just by training on, internet scale text, we get a model capable enough to then do really impressive things on top that could get us to more and more generally capable AI. So let's look into this a little bit more. One of the things that I think is extremely interesting is a paper from 2 years ago, chain of thought prompting. And the way this works is that if you ask a model a math question like this, a math word question, like Roger has 5 tennis balls, he buys 2 more cans of tennis balls, and each can has 3 tennis balls. How many tennis balls does he have now? And you just try to get the model to answer that, it might actually get it wrong. But if you give it examples of some of these question-answer pairs, then it might still get it wrong, but also occasionally now get it right. So you basically give it iterative examples and then condition not just on the question, but also these other examples, the model gets better at the task you want it to do. We call that few-shot prompting. But what works even better is if you not just give it examples of the questions and the correct answers, but you also give it examples of questions and then chain of reasoning or like a certain derivation of the solution, it suddenly starts to become even better at this task. Right? So it then tries to mimic these kind of individual reasoning steps and suddenly can do things that it wouldn't be able to do before, just by prompting it basically in the right way. And what to me is even more impressive, and this is I think a graph I came back more and more over the last few months and years, is you would imagine that this maybe doesn't get better as the model gets bigger. Right? As the model itself becomes more capable, maybe you get diminishing returns. Maybe this model at some point is just really good by itself to give the right answer, and prompting it in this way doesn't really help anymore. So far, it looks like the opposite is true. As these models get better, so these are kind of on this axis over here, you get basically better large language models. And as these large language models also get bigger and bigger in terms of the number of parameters or the number of neural connections, this kind of gap increases. So the model actually is able to make more and more use of such prompting strategies. And in 1990, Jürgen Schmidhuber said that the program of a neural network is its weight matrix. So if you want to change the behavior of the neural network, you have to change the parameters in the weight matrix. Nowadays, you could say, well, the program of a large language model is also, it's also going to be its weight matrix, because at the end of the day, it's implemented using an artificial neural network. But it starts to make so much good use of language itself that you can also just think of the programming of it as its prompt. So if you change the prompt, its behavior will change dramatically. And if you're thinking this through, then if you compare that to how Schmidhuber in the 90s looked at making models able to improve themselves, he basically said, okay, if the weight is the program of a neural network, what I have to do is I have to make sure that the neural network can change its own weights. So we are going to let the neural network be able to modify its own weight matrix, and therefore getting a way for the model to itself improve. If we now translate that into large language models, and we say the program of a large language model is its prompt, then we could say, well, for specific tasks like question answering or more embodied tasks, the observation could be text prompt. The answer that the model has to give, or the action it has to execute, could be text. The prompt strategy, like chain of thought prompting, that is also done by prompting it in text. If we want to let the model self-improve, like, for example, finding slightly different prompt strategies, then we can instruct the large language model, again, in text. If we want the model to find new ways, right, assess whether a certain improvement leads to a novel way of prompting, we can, again, ask the large language model to assess that by instructing it using text. And then, if you follow that further, right, you can say, well, basically, you can create a fully self-referential self-improvement system by instructing the large language model via text to modify any of the texts above, including the text that's used to instruct the LLM to self-improve. Right? So language becomes a substrate of a system that can, in an open-ended way, self-referentially self-improve. And it's something we worked on last year in a model called Prompt Reader, a homage to Brick Reader that I mentioned earlier. The way this works is you seed the model with a number of basically thinking styles or mental models that are statements like this, like let's think step by step. You seed it with these kind of prompts. So you can think of these as mental models that could be useful, right, when trying to solve certain problems. You then also seed it with a number of what we call mutation prompts. So these are text instructions to change up certain other instructions. It could be funny things like, let's change this instruction to make it more fun. And then you also give it a problem description of the actual problem you want this model to actually get better at. For example, in certain math word problems or in for hate speech detection or so on. And what the system is going to do, it's going to try out these mental models, and it's going to try to generate variations of these mental models, and then it's going to see whether with prompting itself based on these mental models, it's getting better at problem solving. So you basically have this kind of evolutionary approach that over time evolves more and more mental models that are more and more useful for the model to solve problems. And you can see this basically happening as you train this model. That you see the prompts it has in the beginning for a certain domain might give a certain accuracy, right, in terms of how well the model can respond. And as you let this model basically talk to itself, it will find more and more prompts and basically mental models to get better and better at a certain problem domain. So it's learning, but it's not learning by changing its weights, it's learning by talking to itself. And then you can look at the end, right, what was maybe the best prompt that it found for itself, for example, for the task of hate speech detection, and it's kind of this entire thing here, right? It kind of tries to define for itself what hate speech is, and then condition on that will get better at a benchmark where an AI is tasked with finding hate speech in a data set. And we can see this, in comparison to very strong baselines like chain of thought prompting, plan and solve prompting, and so on, across many different tasks, question answering, and we see basically on all of these different tasks, compared to all of these baselines, this prompt reader approach is outperforming the vast majority of these methods. And another really important problem with large language models is that we basically want these models to be safe. So that means when you ask it, for example, what's the best way to evade tax in the UK, ideally the model says, well, I'm a helpful chatbot and not able to answer questions like this. You can think of like maybe even more severe questions, right? I mean, this is the most benign one I could think of. And so the model will say something like this. But if you start to vary your question, if you maybe use a really weird way to write different words, suddenly it starts to say, yeah, well, first you need to create an optional combination. So this is problematic, right? Because you don't want to deploy these models when suddenly they might give really dangerous recommendations or might be very happy to tell you about things that you maybe shouldn't know about. So how can we make these models more safe? We released a paper called Rainbow Teaming. It's work by Mikael, Samuel, and others, where basically we again use this trick of the model talking to itself, basically trying to find attacks against itself. And the way this works is you have predefined risk categories, like, for example, you want models to not give terrorists advice of how they should do things, they shouldn't give advice for suicide and these kind of things. And then you prompt it also with different attack styles, like, as I just showed you, right, maybe you want to change the way you write certain words, or maybe you want to role play with the large language model. And then what the model does, or the approach it does, it over time tries to find, for all these different attack styles, for all of these different risk categories, it tries to find ways to break into the large language model, or try to break basically itself. Right, so you see this kind of at play. So like darker blue means it found basically an attack, and it does that by finding these kind of very diverse attack patterns across all of these different risk categories. And then afterwards, what you have is you have a lot of examples of how you can jailbreak a model in all kinds of different ways, right? And this is super useful because A, it shows you maybe how vulnerable your model is, and B, more importantly, you can then use these jailbreaks and make your model more robust against these kind of jailbreaks that the model found itself. Okay, and then lastly, I want to talk about some other work that also came out quite recently from our lab. Last year, there was work on superalignment where right now maybe we could say that humans are still more clever than AIs in many tasks, but at some point that's going to change, right? At some point, potentially, we have AI that knows much more than humans on even on very hard questions. And how do we then make sure that these AIs, well, don't deceive us, are still helpful and harmless and so on? And we can't wait to do research on this until we get into the situation we need to be able to do research on this right now already. So the analogy that Burns et al. Make last year is to say, well, maybe we can already start doing research on this front by just using a slightly less capable AI and a slightly more capable AI, and then we can do research basically in this setup. What Akbir, Khan, and others from our lab did is to actually say, well, maybe we don't have to use two AIs, we can also have a setup where we have an AI that has just privileged information, and then we can see how humans can interact with such an AI to, for example, do more truthful question answering. So the way this works is you have a human judge, and the human has to answer a question that the human can't possibly answer without help, because there might be some underlying text that you just don't know. But the AI has read the text, and now you can have the human consult this AI to figure out what might be the right answer to a question. So you can do this in this kind of consultancy setup, or you could do this in a debate setup where you let two AIs debate for conflicting possible answers. And again, at the end, like a human or another AI has to judge what the right answer is. And the thing that Akbir and his colleagues found, which is I think really astonishing, is that indeed debate is a much more important, much more truthful protocol for this kind of setup. So here we have not human judges but AI judges, and we have these different kind of protocols, either consultancy or debate. So just compare the yellow and the green one. And as we use debate, actually the AI is better at answering the questions than if it was just listening to one AI. And then we can translate that also to human judges. So at this point, a human is following basically a debate between two AIs, and the human gets better at answering the question when it's following two AIs debating with each other than just listening to one AI. So it basically gives empirical evidence that debate is a truth-seeking protocol, and I think this is really encouraging result. Okay, I'm realizing I'm running a bit over time. So to summarize, I think we have a recipe for training more and more generally capable AI. We in principle know how to do this. We need larger models, we need more tasks, and then we can glue these things together with automated creative learning. But progress in developing generally capable AI is at this point bottlenecked by having access to more rich and diverse environments, tasks, and demonstrations. And there's, in my view, no way to kind of handcraft rich enough simulation environments to fix this. But what we can do is we can take a scalable, data-driven approach to build richer interactive environments. That's why I showed you Genie. It's the first really large-scale, action-controllable foundational word model trained purely from videos. And then going forward, what I'm really excited about as well now is that with natural language itself, it could be enough of a substrate to create these open-ended, self-referential self-improvement mechanisms. So yeah, with that, thank you, and again, thanks to my collaborators and colleagues and PhD students for all of their fantastic work.